All right, first off, first most, I need to give credit to Dr. Hua because he most of the content here is from me auditing his class and also asking other people for his notes because I've audited multiple classes before and I've asked other students for their professor's notes because one way or another I want to take anything and everything from a school's knowledge base. Basically, is my plan. Anyways, first thing is I will be explain to you what variability and uncertainty could mean, which is successive observation of phenomenon that do not produce the same result. There's two ways to say it, variability or uncertainty. Another thing I need to talk about is probability model, quantify the risk involved in a statistical inference. For example, the greatest example I can think of, which is the Gaussian distribution, which is very classic and very well known. I think everyone here knows about it because it's been hammered to you all your life. For example, I've recently seen something in LinkedIn where there was like three metal things, which we could do plus or minus uncertainty, but or you can use Gaussian uncertainty, which is pretty cool. And then also a Fourier transform of Gaussian is also a Fourier transform, which is a nice property that you'll learn later on that is really nice. That's really something valuable. Um, Another thing I need to talk about is alert, which is uncertainty associated with randomness, and espenic, which is uncertainty associated with imperfect knowledge. So this is really common and really well known. It's just definitions, and honestly, yeah, that's pretty much what I'm trying to put down right now. It's just, you know. Anyways, we will talk about examples of aleatory uncertainty, which is given like a natural probability, like rainfall data. That is one aleatory. Like, yeah. Anyways, we're gonna go on and talk about aesthetic uncertainty too. Aesthetic uncertainty is like a bend deflection in like a cantilever because there's so many uncertain variables. Uh, we will also need to talk about sample mean, which is over here. Sample mean is necessary because it tells you, the average and the things that mean it's the same math basically. Um, and then with that, we're going to have to talk about histogram here, which is also sample variability too. There's an equation for that, which gives you some, standard deviation. If you take a square root of that, you get that. And I'm going to just quickly draw an example out. Um, it might take me a minute. Yeah, let me, it's not showing up. Uh, what's going on? Um, okay. It's a little laggy, I guess. There we go. There we go. I think it showed up now, hopefully. Beautiful. So I am gonna make this is a real life example actually. I mean, not the not one to one, but it has enough of the yeah, I drew that off scale. We know what, we'll just use a Gaussian distribution to show it off. And with the Gaussian distribution, we kind of know where the mean will. And the bottom section, I think I'm gonna choose temperature, so Fahrenheit, and then the y direction is going to be the number of that times that happen. So we're going to use a mean and, Gaussian distribution. We all know that, the mean is near the average. So let's just approximate it to 60.6 or something. Standard deviation next is what we're going to do. And we're going to just look over here. It's like about 2 blocks away. We need 68%. That's the Gaussian distribution way. So we're going to just say 2. And that's pretty good, right? And then there's, I think, pretty well established. I think that is good enough. Next up, I mean, we can do another example, right? Yeah, I think we need to do another example. I think we're going to do an example that showcases this. I think we'll do a more, I'll give you some numbers, basically, is what my head plan is. I'm just double checking with myself what numbers I should put down. You know what? I'm just going to choose just a bunch of random numbers. And we'll use Desmos to showcase it, the graphing calculator online. Um, hopefully, let me think, 60, 61, 69. 68, 60, 50, we'll get there. Yeah, yeah. Did I just count down? I just count down basically, yeah. Let me just put this in here and we'll just do it. Give me a second for me to finish this up, and then I need to go to Desmo, so just wait a few minutes or seconds. It's gonna be a few seconds of your time. Um, you can skip forward a little bit, I guess. Okay, I got a few numbers, but let me just write this out. I'll paste in a screenshot later. That's for sure I will. Let me make sure I write this correctly. Yeah, that should be correct. Let me grab the screenshot, put it in. Unfortunately, my recording got a little bit of a problematic situation where it didn't record somehow. So I'm gonna have to overlay everything. So we're gonna start again here. I'm trying to show a different way of, showing off graphs. And here's another thing, and this is more powerful when there's like a skew. This is box plot, which is one of my favorite kind of plots because it looks cool, but yeah, it's only good if it's skewed. And the middle line is basically the median, and it can be you know, the first quartile, second quartile, and the last few like out could be different. So be careful. It doesn't have to be in the middle. I drew it as in the middle, but it doesn't have to. Um, so the median is where the 50th percentile is, and the first quartile is 25th quartile, and that's Q1, and the 75th quartile is Q3. So you see how there's like in the middle, there's like 25 and 75 and 100 I showed off, like 50%, like that's what I meant. It doesn't mean that number is 50. I just meant that like there's in the middle, like there's 50% below you and 50% above you. Yeah, and there's Q1 and Q2, like I showed cases. And there's equations here that I showed where outliers can inform. It's Q3 plus 1.5 parenthesis Q3 minus Q1, and then it's greater than that, or less than Q1 minus 1.5 parenthesis Q3 minus Q1. And yeah. We should go on now to heads and tail talk. So head, tail, tail head, and head tail. That's all of the sample space. Event space, which is with the E, sample space with the S. E is for head, and probability is P parentheses E. We know that's a number of count inside E, which is divided by the number of counts inside S. So that's 1 divided by 4 as I showcase over here. Um, yeah. With that said, there's some other stuff we're gonna do as soon as this yeah, we're gonna do the chair analogy, which is basically if a human was to enter the room and try to place which permutation of placement, without any of the human biases, there's three diagonal, which is basically different times. Like you could choose the first, and not time, but different placements. Like you could choose the first, second, and third, and you're leaving with two more. So it's factorial basically, three times two times one. Um, it's kind of what I showcase here, but yeah. And then there's a permutation next, which is basically the same thing but limited. So basically what I'm trying to say is that with the permutation, you can have something like three like candy winners and there's 25 students and no students allowed to take it again, so you can't win twice. So basically in that take what's happening is this shows up and it's basically 25 multiplied by 24 multiplied by 23. And you can get a calculator to get that out. And then we're going to do a combination. But actually, now let me think about what is the number actually. 25 multiplied by 24 multiplied by 23. It's about 1,000, 10,300, 13,800. Yeah, okay. Anyways, per combination. Combinations when we have basically without regard to order, basically. And this the combination is a little bit weird. It shows that there's like a amount of ways you can get it. And then I'll explain it later, but yeah. The permutation result of 25 times 24 times 23 was 13,800, just so you know. Anyways, we're going to use head and tails again. And basically what we figured out is we're going to choose a direction. So I chose to have two tails and one head. And you'll see by these trail batch, there's three ways and eight possibilities. Three divided by eight is basically what happens. But the combination equation only gives you three because it gives you three ways. And I'm going to show this off. I'm going to show this off real quick. Come on. Take it a little bit to show it off. Yeah, but it'll show off soon. Anyways, it'll give you three, and then it'll give you eight. I mean, it'll give you eight possibilities. It won't give you eight. It will only give you three, but you can infer the eight later. But yeah, yeah. You see that? You get three different ways. Yeah. With that said, there's a example of like you know, 50% chance of something breaking, and you use that as an analogy. There's like three different machines that break. So there's like O N N, and then you can do two times two, which is eight, or so forth. So it's two to the power of three, and that makes sense. If you think about how probability works, that is correct. And then this is literally the same math as the coin, just a little inverted because you don't see it, but it's very similar. I'm just giving you an example, but it's the same math. You'll see later on as 3 divided by 8. Um, yeah, I don't think there's any, uh, yeah. Let me just let myself write this whole thing out. Let me just set it. Okay, and I'm going to show arrow to show that same math. Anyway, definitions and terminology of sample points is needed, which we'll see over here. We're going to get a subset, a set basically of E equal to 1, 2, 3, or E equal to HT, and the operator ON, like operating, not operating, or something like that, or in a continuous set where E equals X, which is going to be important when we do integrals. Um, that is later on, although it's you can I'm going to do a continuous set of two is less x is less than two and like or greater than no, x is between two and five basically, and it can be equal to five. And then we're doing a subset. No, we're doing a some kind of yeah subset idea. This is a certain set. The first one is saying that everything is in everything, so it's S equal to E. Or or you can just I didn't explain the bar yet. I guess I should have explained the bar there. But if you put a bar on top, it means not that. So over here you can see that the basically that S is everything, and then E is the inside, and then the outside is E bar. E bar means not in that set, basically. And here we're going to just play a little bit. Basically, we have a bunch of different like unions and intersections, and we just play a little bit with the visual representations of the whole thing, which is really cool. Like we start with the intersection, which is awesome. I mean, you always love a good intersection. The another way to write intersection is E1, E2. Basically, you get rid of the upside down U and just smash it together. I don't think I write it here, but later on I write it like that. Um, it's no different than writing the the intersection sign, which is the N. Did I? Yeah, I did not. But you'll see me write that later on, which I should have explained earlier, but I did not. Um, okay, so yeah, I think yeah. I don't know which one I was doing here, but I was playing with more of these things, which should have been. Oh, yeah, this one is showcasing if E1 and E2 is here, what can you make it equivalent? So if you make it opposite, like everything, then it shows the whole entire thing. But you can also, instead of doing that, you can use a union, and you can make a bar on that union individually. Because if you think about it, it's a little bit visualization, but it does cancel out to everything else. Um, it works. Um, yeah. Uh, I wish I was doing it alongside you, but the audio got cut, so I'm doing this a little bit of awkward way where I'm speaking after the fact, so it's kind of a little harder. I think this is where I do a little bit of properties, like community property, associate property, and addition property, and I believe it was called, I forgot, some other property I did. I believe conditional property. Yeah. So I was showcasing how you can do showcase the individual division property of this, and it's pretty cool.